Hi, so in this clip video, we'll talk about how to implement, how to write graph algorithms in C++. But basically, we'll start with how to, a quick review on how to represent a graph as a data structure in your code. So basically, there are two ways. I hope that in the lecture, you've learned both of them. One is given this graph, the first way to represent the graph is through uh, adjacency matrix. First represent matrix. Okay, so basically you have a matrix. So if you have n nodes, so here we have 6 nodes, right? In this example, n equals 6. So you're gonna have an n by n matrix that represent how these nodes are connected. Okay, so basically you're gonna have 0 1 2 3 4 5. So I'm gonna number my nodes starting from 0 because it would be nice with our data structure inside our C++ code. But basically in the task statement usually they start with 1, so we need to convert it a little bit, but if we keep everything starting from 0 and only convert the numbers when you read inputs and print output, it will be consistent and it will be nice inside your program. Okay, so basically, okay, I'm gonna have, okay, and then if there's an edge, so the first example, we have an undirected graph. So an edge represent the relationship that go both ways. So if you have an edge between 0 and 1, so it means 0 can go to 1 and 1 can go to 0, so it's undirected. Okay, so basically we gonna, if there's an edge you put 1, if there isn't an edge you put 0. So let me just put all the ones. Okay, so 0 connect to 1, so it's 1 here, and 0 connects to 5, like that. And you can do it all, right? So let me do that really quickly. Okay, so let me quickly write 0. Everything else is 0. Okay, so this is the adjacency matrix representation of this graph. So if you want to see if there is an edge between 0 and 1, right, between this pair, which there is, right? So you look at 0 and 1 here, or 1 0, it's undirected. And if you want to check if 0 and 2 has an edge, so you look at 0 and 2 here, there's no edge, or 2 and 0, right? Okay, is there an edge between 4 and 2? So you look at 4 2 here, there's an edge, right? Or 2 4, same thing. Okay, 2 4. Okay, is there an edge between 5 and 3? So you look at 5 and 3, no edge, or 3 and 5, right? No edge like that. So basically you can check pretty quickly if there's an edge between any pair of nodes. Okay, but this adjacency matrix representation is pretty bad in terms of memory. And if you want to look at the number, like figure out, iterate all the edges that is adjacent to a particular vertex, it would take on, because you need to basically go through all the entries in a row, right? So it's good for checking if there's an edge or not. Okay, checking edge can be done in O1, but space required is gonna be on square. If you have a lot of edges, then that would be fine, but if you only have a few edges, the space required is pretty large. And to look at iterate all edges adjacent to a particular vertex u, that would take O of n as well, because you have to read the whole row. Okay, now another way to represent a metric as a data structure is called an adjacency list. So let's take a look at that really quickly. The second way is called adjacency list. Okay, so instead of having the whole matrix that represent the whole graph, you only keep the edges. Okay, so basically you have a list for each vertex. You have vertex 0, 1, 2, 3, 4, and 5, and you keep basically the list of vertices with an edge from that vertex. Say vertex 0 is adjacent to vertex 1 and 5, so you put 1 and 5 there. For 1, you basically put 0 and 5. For 2, it's going to be 3, 4, 5. The order doesn't really matter, so I'll just write them down somewhere. This 4 and 2, right? For 4, 2, 3, 5. 2, 3, 5. For 5, it's going to be 0, 1, 2, 4. Okay, you can keep, so that's the actual data. You can keep it in as a linked list, okay, or as a vector. Okay, so basically you're gonna have a linked list. If you want to do it as a list, actual list, you can have a linked list. Or in C++, we typically keep we store it as a vector of int. In our code example, we will look at that. Okay, now good thing about adjacency list is that the space required, okay, it's going to be OM, where M is the number of edges. So in this case, 1, 2, 3, 4, 5, 6, 7, 8. M is 8. So the space required is order of M. So here you're going to keep 16 number, right? 1, 2, 3, 4, 16 numbers, because each 8 contribute to 2 items. Okay, but so space requires OM. And if you want to look at the edges, the adjacency, the nodes adjacent to a particular vertex, it's gonna be iterate over adjacent vertex nodes of u. It's gonna take time or degree of u. The degree of a vertex is the number of edges adjacent to it. Like this one, the degree is 2. This one is 2. The degree of this guy is 4. Okay, so you have to just go through the list like here. So the number of edges that is adjacent to it is so it's linear in the number of edges that is adjacent to this vertex. Okay, so this particular representation is the one that we use, is the preferred one, because the space required is good, and when we implement breadth first search or depth first search, it will give us a linear time algorithms that would run in times O n book m. So that's the number of nodes plus the number of edges. If you represent the graph as an adjacency matrix, the algorithm would run in O n square, and that would be really slow. Okay, so if you have say 100,000 vertices and like maybe 200,000 edges, if you implement the thing in adjacency list, it will be really fast. But if you keep the thing as an adjacency matrix, you probably don't have enough memory for that, because 100,000 what is this? So the space will be square of that, and that's you probably don't have enough memory to keep that. Okay, so it's impossible to keep that in your memory as well. So basically we keep an adjacency list. So the bad thing about adjacency list is that if you want to check if a particular edge is in the graph, then you really you can't do it in O1. Okay, you need to go through all the lists, but you can use data structure like map or set to help you doing that. When we look at that in STL, we'll see more example of that later on. Okay, so this is the way we're going to keep our graph. So as an example, let's see another representation of this directed graph. So a directed graph is a graph with direction. So basically, instead of typically using a line segment as an edge, we have arrows. Okay, so in this case, the graph will be represented like this. So 0, 1, 2, 3, 4, 5. So it's gonna be asymmetric. So if there's an edge from 0, it might not have an edge from 0 to 1. So in this case, we will put the edges from 0 to 1 like that. But you're not gonna, from 1, you're not gonna have an edge to 0. So the list will look like that. From 1, let's go to 5, 4, and 2. It's gonna be 5, 4, and 2. From 2, it's gonna be 1. Okay. Only one outgoing edge. Okay. From 3 to 1 and 2. From 4 to 5 and 3. Then from 5 to 4. And that's it. Okay. So this is how we're gonna keep the directed graph. Okay. So now, how are we gonna write C++ code for keeping this kind of graph? So the idea is that we're gonna keep this kind of thing, okay, as a list. But a list is pretty is quite inefficient to implement in C++. Even though your code will pretty much look the same, but the running time will be different. So we basically use a vector. So the idea is that we're gonna keep an array of vectors for the whole thing like this. We'll see the code, and we also keep str vectors. We might keep an array of degree in the graph so that when we look at the edges adjacent to one particular vertex, it will be easier to deal with. Okay, but you can just use function size, member function size of vectors to get the degree as well. But I usually keep another variable called degree for keeping the degree of the vertex. Okay, so this is the idea on the representation. Okay, so before we look at the algorithm on graphs, let's take a look at how to write C++ code to read a graph and keep it as a data structure inside your code. All right, so let's start by looking at the actual programming task. So this is the first practice task called connected components. So the idea is that you want to count the number of connected components. If you don't remember, the connected components is the number of intuitively you're given an undirected graph and you want to see how many connected pieces in the graph. So let's look at one example. So suppose this is your graph. You can think of them as a way to say which node is connected to which nodes. And the number of connected component in this graph is basically, this is the first connected component, the second one, third, fourth, fifth one. So there are 5 connected components. So before we can actually solve the task, we need to actually read the input first. So let's take a look at how the input format of the graph. Okay, so this is a typical way to read and to input a graph. So basically, you're given 2 numbers. One is number of nodes, n, and another is number of edges, m. And then the nodes are labeled from 1 to n. Okay, so in our previous example, I start with 0. So this is how we're gonna keep our data structure internally. So we usually start with 0. When the input start from 1, you can do many things with it. Okay, typically the way I usually do is that when I read the node number, I just I immediately decrease it by 1 so that it will start in my code. Everything start with 0 always. When I want to output, I'll check again if I need to add 1 or not. Okay, all right, so and then the next m line, so the first line is number of nodes and edges, and the next m line are list of edges. Like this 1 2 is that node 1 is connected, that's an edge from 1 to 2, 2 to 3, 3 to 1, 4 to 5, something like that. Okay, and the number of connected components is 2. So let's see one example for that. So for input 1, the graph would be like this. you start with from 5 vertices, 1, 2, 3, 4, and 5. Okay, 1, 2, 2, 3, 3, 1, and 4, 5. So there are 2 connected components there. Let's look at another example here. So you have six vertices, 1, 2, 3, 4, 5, 6. Okay, 1, 2, 2, 3, 3, 1, and 4, 5. So here you're gonna have 3 connected components because this guy's on its own, right? Okay. The way we're gonna keep everything inside our code is that we're gonna have an adjacency list, okay, representation. But I'll change inside my code again. So I'll put this 1, decrease it by 1, okay, so that everything starts with 0. Okay. Now the way I'm gonna do it is to use a vector. So let's see how I'm gonna do it. Okay. So to use a vector, so you need to include vector like that, and I need to read input. So I say include IO stream, and because I'm lazy, I usually use name space std. Okay. Then I need n and m, right? That's the number of nodes and the number of edges. Furthermore, I'm gonna need an array of vectors. Okay, so each adjacency list I would keep them as a vector of int, but then there are n vertices, right? So I need an array of vectors to keep a bunch of lists. Let's see. So the limit is that n is 100,000. So I usually do this const in max n equals like this. But usually I add 10 so that if I made a mistake, I won't kill myself. Okay, so I have an array called adj. That's an adjacent. So this is basically a bunch of vectors. Okay, for each vertex you have 1 vector to keep the adjacency list of that vertex. So if you look at our example previously, so one vector is for this whole list. Okay, 1 vector is for this whole list. So it will be this thing is gonna be adj 0. That would keep 1 and 5, and this is gonna be adj 1, something like that. Okay, so one vector for 1 list. Okay, that's it. Okay, that's the data structure. Furthermore, I usually have this array called degree that I would initialize to 0 to keep the degree of the vertex. It will be handy when you need it, but you don't really need it. Okay, so if you have a vertex you can just call editju.size. That would give you the degree as well, but I'm pretty lazy about that. Okay, so let's write main. Our main program would read n and m. So let's create a function, read input. Okay, so we start by cin n, read n and m, and then let's see. Okay, the first line has n and m, right? And then m lines are lists of edges. So for I equals 0, I less than m, I equals u and v. It's called u and v. And then I read u and v. So there's an edge from u to v and v to u because this is undirected graph. If in this task it's not clear is it undirected or not, but it's undirected. Okay, because when you talk about connected component, usually you look at the undirected graph. Okay, so you need to add an edge from u to v and v to u. Okay, but before doing that, recall that in the task statement, the number of nodes u and v start with 1, right? But we'll keep everything 0 base. So I usually do this right away before I start doing anything at all. Okay, so now I need to put v at the end of the list for u. So I call ADJU pushback like that. Okay, now I need to deal with the degree, so I usually say degree U plus plus degree V plus plus like that here. Okay, if the graph is directed, I just delete these two lines. Okay, if the graph is directed, then you have U to V, you don't put V to U back. Okay, but if the graph is undirected, you need to put two edges like that. Now you need to clean up the degree array. You can, when you write it like this, I hope it will be zero fill, but I'm not sure, so I need to for a plus plus, and then I would say degree I equals 0 like that. Okay, or I usually use U and V as indices to represent the vertex, the nodes. So this is how I'm gonna write it. If you are good with C++, you can just call fill degree plus n 0 like that. So it will fill the array for you. But let's keep it this, simple this way. Okay. So this is how you read the graph. Next, we will look at how to implement a breadth first search. Okay, using the data structure that we have just read the graph into. Okay, so in our main program, we just call read input. Okay, and then we'll do breadth first search, starting some vertex 0. Okay, from this, we'll look at all the vertices that are reachable from vertex 0. Okay, and if you want to count the number of connected components, you need to call BFS that many times. Okay, so I'm going to give you a hint, but I'm not going to write the whole thing for you. Okay, so let's check back on how the breadth first search works, and then we'll write the code.